In today's lesson, we're going to talk about point-slope form of a linear equation. In the last lesson, we spent the entire time talking about slope-intercept form. Now we're going to talk about a new form, point-slope form, and make some comparisons back to slope-intercept form. By the end of the term, you should be able to write the equation of any line, whether you're given a slope and an intercept, 2 points on the line, a graph of the line, or a verbal description. I'm going to talk about the development of point-slope form. Then I'm going to find some linear equations given 2 points on a line, starting out with point-slope form. And then I'm going to find a linear equation given a graph of a line. So let's start by developing point-slope form. Let's think back to our equation for finding slope. If we have 2 points on a line, x sub 1, y sub 1, and x sub 2, y sub 2, we can use our slope formula to find the slope m. I'm going to make a slight change here. That point, x sub 2, y sub 2, I'm going to think of as being any point on the line. To do that, I'm going to get rid of the subscripts. So the x sub 2, y sub 2 is just going to become xy. And now xy can be any point on the line other than the point x sub 1, y sub 1. Well, let's go back to the formula. If I wanted to clear the fractions from the formula, I would multiply both sides of that formula by the denominator, x minus x sub 1. When I do that, I end up with m times x minus x sub 1 equals y minus y sub 1. This is what we call point-slope form. We usually write it the other way, though. We usually write y minus y sub 1 equals m times x minus x sub 1. So the point-slope form of the equation of a line is y minus y sub 1 equals m times x minus x sub 1, where m is the slope of the line, and x sub 1, y sub 1 is a fixed point on the line. Let's think back to our diagram. X sub 1, y sub 1 is that lower point on the line. That's fixed. We talked about how xy could be any point on the line. In fact, xy gives us all of the solutions to the linear equation. Xy could actually be the point x sub 1, y sub 1. If that were the case, in my formula, if y and y sub 1 had the same value, the left-hand side would be 0. And if x and x sub 1 had the same value, the right-hand side of the equation would also be 0. The slope m times 0 equals 0. And we get 0 equals 0 for the equation. That tells us that xy is a solution to the equation, even if xy is the point x sub 1, y sub 1. So let's look at some examples finding a linear equation given 2 points on a line. Let's use the point-slope form to find the equation of the line that passes through the points negative 2, 3 and 2, 15. We're going to write our equation in the form y equals mx plus b. So in this example, I'm going to start out with this new point-slope form. But when I get to my final answer, I'm going to write it in slope-intercept form. So I have 2 points on the line, negative 2, 3 and 2, 15. Whenever I have 2 points on a line, I can find the slope. So let's go ahead and do that. Our slope, m, would be 15 minus 3 over 2 minus negative 2. That's 12 over 4, which is 3. Remembering the point-slope form we just developed, y minus y sub 1 equals m times x minus x sub 1. So I've just found that the slope is 3. The other thing I need in the point-slope form is a point. I can use either one of these points. I'm going to make the point 2, 15 x sub 1, y sub 1. In determining the slope, it doesn't make any difference which point I call x sub 1, y sub 1. And I could use negative 2, 3, which I did in determining the slope as x sub 1, y sub 1, but still call 2, 15 x sub 1, y sub 1 when I'm finding the formula for the line using point-slope form. So let's fill in our formula. Y sub 1 is 15, so I have y minus 15 equals m is 3 times the quantity x minus x sub 1 is 2. So here's the formula for the equation of the line in point-slope form. We're asked to write the answer in the form y equals mx plus b, that is slope-intercept form. So let's solve this equation for y. I'm going to distribute the 3, which gives me y minus 15 equals 3x minus 6. Then I'm going to add 15 to both sides of the equation. So y equals 3x plus 9. This is my proposed equation of the line passing through the points negative 2, 3 and 2, 15. I actually want to do a little bit of a check here, so I just came up with y equals 3x plus 9. I used the point 2, 15 to find the equation. I want to make sure that the point negative 2, 3 also lies on this line. So for my check, I'm going to let x equal negative 2 and find out whether or not y equals 3. So if x equals negative 2, then y would be 3 times negative 2 plus 9. That's negative 6 plus 9, which is 3. That's exactly what we wanted. This shows the point negative 2, 3 also lies on the line. So I can write my conclusion. The equation of the line is y equals 3x plus 9. Well, let's think about what would have happened if we looked at the other point in our point-slope formula. I arbitrarily decided that x sub 1, y sub 1 was going to be the point 2, 15. What if I now consider the point negative 2, 3? Well, we've already determined that the slope is 3. So let's use y minus y sub 1 equals m times x minus x sub 1, but this time making x sub 1, y sub 1, the point negative 2, 3. So I'd have y minus 3 equals a slope of 3 times x minus negative 2. I want to go ahead and solve this for y. So y minus 3 equals 3 times the quantity x plus 2. Distributing 3, I have y minus 3 equals 3x plus 6. Adding 3 to both sides, I have y equals 3x plus 9. I'm pretty sure that's what I got when I used the point 215. Let's go back and check. The equation of the line is y equals 3x plus 9. It doesn't make any difference which point on the line I choose in the point-slope form. So let's look at another example. This time we're asked to use point-slope form to find the equation of the line with t-intercept 5, 0 that passes through the point 3, negative 4. And we're asked to write our answer in the form z equals mt plus b. So once again, we're going to start in point-slope form, but our final answer is going to be in slope-intercept form. So this time, when I think about the point-slope form, I need to use the variable z as my dependent variable. So I have z minus z sub 1, and the variable t as my independent variable. So equals m times the quantity t minus t sub 1. So I know in point-slope form, I need a point. I have 2 of those, and I need the slope. So let's go ahead and compute the slope. So my slope is going to be negative 4 minus 0 over 3 minus 5. That's negative 4 over negative 2, which is positive 2. Now I can choose either point. I'm going to look at the point 5, 0. Substituting the slope of 2 and the point 5, 0 in the point-slope form, we have z minus 0 equals 2 times the quantity t minus 5. Solving for z, we just get z equals 2t minus 10. So my proposed linear equation is z equals 2t minus 10. So let's check to make sure that this equation really works. Z equals 2t minus 10. So I used the point 5, 0 to find this equation. For my check, I'm going to use the point 3, negative 4. So in my check, I'm going to let t equal 3 and find out whether or not z equals negative 4. So if t equals 3, then z equals 2 times 3 minus 10, which is 6 minus 10, which is negative 4. So this checks. So I can go ahead and write my conclusion. The equation of the line is z equals 2t minus 10. So now let's look at finding linear equations given graphs of the line. Here we have a mystery line in figure 1, and we're asked to find the equation of the line graphed below. I'm still thinking about point-slope form, which we have just developed. I have 2 points that I can see on the line. Looks like -1, 1 and 4, 5. I can use either one of those points in point-slope form. What I also need, though, is the slope. Now I could use these 2 points to actually calculate the slope with the slope formula, or I can use the graph to figure out what the slope between these 2 points is. So if I start at the point -1, 1, it looks like I have a rise of 4 and a run of 5. So a slope of 4/5. So point slope form, y minus y sub 1 equals m times x minus x sub 1. If I use the point 4, 5 and the slope 4/5, this becomes y minus 5 equals 4/5 x minus 4. Let's go ahead and put this equation in slope-intercept form. So let's solve the equation for y. I'm going to distribute the 4/5. So I have y minus 5 equals 4/5 x minus 16/5. And then I'm going to add 5 to both sides of the equation to isolate y. So that would give me y equals 4/5 x minus 16/5. And I'm adding 5, but I'm going to add it in the form 25/5 so that I have a common denominator. So simplifying, I have y equals 4/5 x plus 9/5. Well, before I go through and do a formal check, the first thing I want to do is look at the graph and notice that 9/5 looks like the place where this graph crosses the y-axis. So it seems reasonable that the y-intercept would be 9/5. And here I have a b value in slope-intercept form of 9/5. Well, let's do a formal check. So I came up with y equals 4/5 x plus 9/5. Let's look at the other point that's easy to see on the line, -1, 1, and make sure this satisfies this equation. So if x equals -1, I'm hoping y is going to equal +1. If x equals -1, then y equals 4/5 times -1 plus 9/5. 4/5 times -1 is -4/5. When I add that to 9/5, I get 5/5, which is indeed 1. So this checks. The point -1, 1 is a solution to this linear equation. So I can go ahead and write my conclusion. The equation of the line is y equals 4/5 x plus 9/5. Let's look at another example. This mystery line has some labels on the axes. It looks like we're looking at speed in feet per second versus time in seconds. Let's look at a couple of points on the line. For instance, it looks like 1:20 is a point on the line, and it also looks like 2:30 is a point on the line. Thinking about the slope here, it looks like I have to rise from 20 to 30. That would be 10 with units of feet per second, and run from 1 to 2, that's just 1, with units of seconds. So my slope is 10 with units of feet per second per second. So let's go back to our point slope form and use the variables s and t. So we would have s minus s sub 1 equals m times the quantity t minus t sub 1. And let's pick one of our points. How about this top point, 230, that we have marked here? So we would have s minus 30 equals the slope, the numerical value is 10, times t minus 2. Let's go ahead and solve this for s, so our equation will be in slope-intercept form. So s minus 30 equals 10t minus 20. Adding 30 to both sides, we have s equals 10t plus 10. Well, let's look at this. We have s equals 10t plus 10. This is slope-intercept form. It tells us that the slope is 10 and b is 10, which means our vertical intercept should be 0, 10. Look at the graph. On the graph, it definitely looks like the vertical intercept is 0, 10. In fact, it probably would have been easier just to write this equation using slope-intercept form. We found the slope to be 10, and we can see clearly on the graph that the vertical intercept is 10. Let's go ahead and be double sure and check another point on the graph. So we came up with s equals 10t plus 10. I'm pretty sure this is correct because I calculated the slope, I believe in my calculation, and I can see the vertical intercept of 0, 10. But let's look at another point on the line. 120 is also a point on this line. So for my check, if t equals 1, s better equal 20. Well, if t equals 1, then s is 10 times 1 plus 10. That's 10 plus 10, which is 20. So this does indeed check as I expected it would. So I'm going to go ahead and write my conclusion. The equation of the line is s equals 10t plus 10. Let's look at another example. In this mystery line, it looks like we're looking at height in feet on the vertical axis depending on time in seconds. And let's learn a lesson from the last example that we looked at. Looking at the graph, it seems pretty clear to me that the vertical intercept is 0, 150. So I think instead of starting in point slope form this time, I'm just going to use slope-intercept form to write the equation of this line. So I should have something of the form h, my dependent variable, equals mt, my independent variable, plus 150. I know the value of b is 150 because my vertical intercept is 0, 150. The only thing left to find here is the slope. So let's find the slope between a couple of points on the line. How about the point 1, 100, and 250? It looks like I have a rise of negative 50, and that's measured in feet, and a run of 1 second. Negative 50 divided by 1 is just negative 50, so my slope is negative 50 feet per second. So h here should be negative 50 t plus 150. Let's go ahead and check this. So we have h equals negative 50 t plus 150. Let's pick one of the points on our line. How about the horizontal intercept, since that also seems clear from the graph? Our horizontal intercept is 3, 0. Does this satisfy the equation? Well, if t equals 3, we're hoping h equals 0. If t equals 3, then h is negative 50 times 3 plus 150. Negative 50 times 3 is a negative 150. Negative 150 plus 150 is 0. So indeed, this does check, and I can go ahead and write my conclusion. The equation of the line is h equals negative 50t plus 150. Let's look at one more graph here. The first thing I notice on this graph, since I've just been focusing on vertical intercepts, is it's not too clear to me exactly where the vertical intercept is. Definitely lies somewhere between 50 and 100, probably closer to 100, but I'm not sure where that is. So I'm going to revert back to point-slope form to find this equation. I can see here that we have heating costs measured in dollars depending on temperature. And looking at this graph, it's really easy to read this graph backwards and think about, as the temperature goes down, the heating costs go up. And I'd actually even be following the arrow here. What we need to remember, though, when we're reading graphs is we always read from left to right. So what we want to think about is, as the temperature goes up, the heating costs go down. This is a decreasing line. I would expect a negative slope. Decreasing lines have negative slopes. So let's determine what the slope would be here. Looking at the point negative tan 100 and the horizontal intercept 40, 0, it looks like I have a rise of negative 100, and this is measured in dollars, over a run of 50, and this is measured in degrees Fahrenheit. Negative 100 divided by 50 is negative 2, so I have negative $2 per degree Fahrenheit. Now I should be able to use either point on the line in point-slope form. Let's use the point negative 10, 100. So our point-slope form is going to be c minus c sub 1, there's my dependent variable, equals m times t minus t sub 1. So using the point negative 10, 100, we have c minus 100 equals m, that's negative 2, times t minus t sub 1 is negative 10. Let's go ahead and write this in slope-intercept form. So let's solve this equation for c. So I have c minus 100 equals negative 2 times t plus 10. And let's distribute the negative 2. So c minus 100 equals negative 2t minus 20. And add 100 to both sides. So c equals negative 2t plus 80. Well, before I started all of this, I said it wasn't clear exactly where the vertical intercept is. But it does seem reasonable that b is 80, that the vertical intercept is 0, 80. That's between 50 and 100, and closer to 100, which is what I predicted. So let's go ahead and check our equation now. We came up with c equals negative 2t plus 80. I used the point negative 10, 100 to find the equation, so I'm going to use the point 40, 0 to check. So in my check, I'm going to let t equal 40. So if t equals 40, then c equals negative 2 times 40 plus 80. Negative 2 times 40 is negative 80. When we add negative 80 to positive 80, we get 0, which is exactly what we wanted. The point 40, 0 is a solution to this equation. So I can write my conclusion. The equation of the line is c equals negative 2t plus 80. Well, one last thing with this same graph. Let's show that the units work out. We've already found that the slope, m, is negative $2 per degree Fahrenheit. We know that c, the heating cost, is measured in dollars. And we know that t, the temperature, is measured in degrees Fahrenheit. Let's take a point on this line. Let's go back to our point negative 10, 100, and show that all of the units make sense in our formula. So our formula is c equals negative 2t plus 80. If I have a heating cost of $100, and my slope has units of dollars per degree Fahrenheit. I'm going to make a little bit of room here so I can fit this. And I'm putting in a temperature of -10 degrees Fahrenheit. Then I have this b, the plus 80, hanging at the end. Well, the b tells me about my vertical intercept. My c value of the vertical intercept is 80, and c is measured in dollars. So this 80 is also measured in dollars. So I have $100 on the left, and hopefully the units on the right-hand side also simplify to dollars. Let's take a look. When I'm multiplying -2 dollars per degree Fahrenheit by -10 degrees Fahrenheit, the degrees Fahrenheit cancel, and I'm just left with dollars as my units. -2 times -10 is 20, with units of dollars. And to that, we're adding $80. $20 plus $80 is $100. The units work out. Well, let's go back to our point-slope form again. What's the slope of the line y minus 3 equals 5 times the quantity x minus 2? And what's a point on this line? Recall that the point-slope form of the equation of a line is y minus y sub 1 equals m times the quantity x minus x sub 1, where m is the slope of the line and x sub 1, y sub 1 is a point on the line. So in our equation, the 5 looks like it's the value of m. That part's easy to read. We have y minus 3 equals 5 times x minus 2. What about our point, x sub 1, y sub 1? Well, y minus y sub 1, it looks like y sub 1 is 3. X minus x sub 1, it looks like x sub 1 is 2. So I would say the slope is 5, and a point on the line is 2, 3. So notice that if xy equals 2, 3, the equation becomes 0 equals 0. Look at our equation. If we replace y with 3, we have 3 minus 3 is 0 on the left-hand side. If we replace x with 2, we have 2 minus 2 is 0, multiplied by 5 is still 0 on the right-hand side. So 2, 3 is indeed a solution to this equation, which means 2, 3 is a point on the line. Let's look at another example. What's the slope of the line y plus 1 equals 2 times the quantity x minus 4, and what's a point on this line? Thinking of our point-slope form again, it seems fairly obvious that the slope is 2, since that's being multiplied by the quantity x minus 4. What's a little bit trickier here is determining a point on the line. In the formula, we have y minus y sub 1, but in my equation I see y plus 1. The signs are different. So I think I'm going to rewrite this as a subtraction on the left-hand side first to help me determine what y sub 1 is. So y plus 1 can also be written as y minus the opposite of 1, y minus -1. So another way I could write this equation is y minus -1 equals 2 times the quantity x minus 4. So it looks like y sub 1 is -1 and x sub 1 is 4. So I can say the slope is 2, and a point on the line is 4, -1. Now let's make another quick observation. If xy equals 4, -1, this equation becomes 0 equals 0. If we replace y with -1, the left-hand side becomes 0. If we replace x with 4, the right-hand side becomes 0. So we just looked at a couple of equations here. In the equation y minus 3 equals 5 times the quantity x minus 2, we said 2, 3 was a point on the line. In the equation y plus 1 equals 2 times the quantity x minus 4, we said the 4, -1 was a point on the line. What about the equation y plus 6 equals 2 times the quantity x plus 7? Well, if we think about what will make both sides of this equation 0, if y were -6, the left-hand side of this equation would be 0. If x were -7, the right-hand side of this equation would be 0. So -7, -6 is a point on this line. Notice that if we rewrite this as y minus -6 equals 2 times the quantity x minus negative 7, again we can see x sub 1, y sub 1 is negative 7, negative 6. So now I want to turn this over to Anne, who's going to look at some parallel and perpendicular lines and discuss point-slope form some more.
In this part of the lesson, we're going to be finding the equations of more lines. We're going to use point-slope form and slope-intercept form. So in order to get some practice, we're going to work with parallel and perpendicular lines. So to start, we're going to review the slopes of parallel lines and perpendicular lines. Then we'll work a bunch of examples. We'll work with both slope-intercept form and point-slope form. Then we'll just finish up with one application. So let's review the slopes of parallel lines and perpendicular lines. So non-vertical parallel lines have equal slope. In this picture, we have two lines that are decreasing at the same rate. Perpendicular lines have opposite reciprocal slopes, provided that neither is vertical. So let's work a couple of examples here. We want to find the slope of a line parallel to the line 5x minus 4y equals 20. This is a linear equation given in standard form. We haven't seen one of these for a while. Now the first thing I need to do to find the slope of any line parallel is to find the slope of the given line, because parallel lines have the same slope. There's two ways I can do this. I can find two solutions to the equation and calculate the slope that way, or I can convert the equation to slope-intercept form and read the slope off the equation. For this example, I think I'm going to find two solutions, because here the intercepts are very easy to determine. So for example, my x-intercept will have a y-coordinate of 0, and my y-intercept is going to have an x-coordinate of 0. So plugging numbers into my equation, when y equals 0, I just have 5x equals 20. So x has to equal 4. If I substitute 0 for x in my equation, then I have negative 4y equals 20, so y has to equal negative 5. So I can very quickly determine two solutions to this equation. So the slope of a parallel line is going to be the slope of this line. And the slope of this line is going to be the difference in the y values over the difference in the x values. This is negative 5 over negative 4, which is 5/4. So the slope of any line parallel to the line 5x minus 4y equals 20 is 5/4. Let's do an example with perpendicular lines. Now I want to find the slope of a line perpendicular to the line 3x plus 2y equals 19. I first need to figure out the slope of this line. Now here, if I think about the intercepts, I start thinking about fractions. Maybe I don't want to go there. So I'm going to solve this equation for y and put it into slope-intercept form. So my equation is 3x plus 2y equals 19. I'm going to isolate y. So I'm going to start by subtracting 3x from both sides. Now I can divide both sides of the equation by 2. And 19 divided by 2, that's 19 halves, or 9.5. And 3 divided by 2 is 3 halves, or 1.5. So there's a couple ways I can write this equation. I can put the negative 1.5 x plus 9.5, or if I'm thinking about rise over run, I might want to work with fractions. But now I have the equation in slope-intercept form. I see that the slope of the given line is negative 3 halves. We want to find the slope of any line perpendicular. That's going to be the opposite reciprocal. So the slope of any perpendicular line is positive 2/3, the opposite reciprocal of negative 3/2. Let's do a graphical check of this. So I have the graph of 3x plus 2y equals 19. Let's just see that a slope of 2/3 will give me lines that are perpendicular. So I'm just going to choose a point on the given line and graph a line with a slope of 2/3. So rise 2, run 3. The scale on each axis is 1 here. Rise 2, run 3. If I pull out my ruler and graph the line containing these 3 points, it certainly does appear to be perpendicular. So now we're going to do some examples working with both slope-intercept and point-slope form. In the next example, slope-intercept form is used when the given line is stated in slope-intercept form. And I'm going to use point-slope form when the given line is stated in point-slope form. Now there's no rule that prescribes that this is the way to do these types of problems. This is just an opportunity for us to practice working with both forms of the equation. So here's the first example. We want to find the equation of the line parallel to the line y equals negative 3x plus 5 that contains the point 2, 3. Well, I know what the slope of the parallel line is. It's got to be negative 3. So I'm looking for an equation of the form y equals negative 3x plus b. My given line and the line I'm looking for have the same slope. They're parallel. Now I need to find b. Well, to find b, I'm going to use the point on the line. It must satisfy the equation. So if x equals 2 and y equals 3, then replacing 3 for y in my equation and 2 for x will allow me to determine b. So I have 3 equals negative 6 plus b. So b equals 9. So my equation should be y equals negative 3x plus 9. Let's do a check. I have a graph of the line y equals negative 3x plus 5. That's the line I started with. I want to see that the equation I came up with does indeed contain the point 2, 3 and is parallel to the given line. So I know the vertical intercept is the point 0, 9. The slope is negative 3. So I'm going to go down 3 to the right 1, down 3 to the right 1, down 3 to the right 1. One of the things I noticed is when I was finding points on my line, I hit that point 2, 3. Now let me connect these points to show that the two lines are indeed parallel. Looks pretty good. So stating a conclusion, the equation of the parallel line is y equals negative 3x plus 9. Let's do another example. Now here we're given an equation in point-slope form. We want to find the equation of a line parallel to the given line that contains the point 4, 4. Well, here in point-slope form, we just have to fill the missing constants into our equation in point-slope form. Well, the parallel line is going to have the same slope as the given line. So I know the slope's going to be 2. I'm given a point on the line. So I know that x sub 1, y sub 1 equals 4, 4. So plugging things into my equation, the parallel line is going to be y minus 4 equals 2, x minus 4. Now I can solve this equation for y to put it into slope-intercept form. So I have y minus 4 equals 2x minus 8. So y equals 2x minus 4. This line should be parallel to the given line and contain the point 4, 4. So let's do a graphical check. I've graphed the line y minus 3 equals 2 times the quantity x minus 1. Now the point 1, 3 is on the given line. I can see that from the form of the equation, and the given line does indeed have a slope of 2. Now I want to graph my line, which was y equals 2x minus 4. Just double checking there. So now the vertical intercept is the point 0, negative 4, and my line has a slope of 2. So I'm going to go up 2 to the right 1, up 2 to the right 1, up 2 to the right 1, and if I do that one more time, I land on the point 4, 4, which is what I wanted. And when I connect those points on my line, I should see a parallel line. Well, that's as good as parallel gets with my hand-drawn graph, but I'm pretty convinced I have the right line here. Now let's work with some perpendicular lines. Now my given line is y equals negative 4x plus 6. I'm asked to find the equation of the line perpendicular to this line that contains the point 5, 0. So the slope of the given line is negative 4, which I can think of as negative 4 over 1. So the slope of the perpendicular line will be the opposite reciprocal, and that's going to be positive 1/4. So using slope-intercept form, I know that y equals 1/4 x plus b. I just have to determine b. So I know that when x equals 5, y equals 0. This has to be a solution to my equation. So if x equals 5 and y equals 0, then I have 0 equals 1/4 times 5 plus b, or b equals negative 5/4. So my equation should be y equals 1/4 x minus 5/4. Let's check this with a graph. So my equation was y equals 1/4 x minus 5/4. Now to graph this, I want a point on the line y equals 1/4 x minus 5/4. The vertical intercept doesn't land on integer coordinates, so my grid is all labeled here in integers. So I think I'm going to look for another point on the line. For example, what happens if x equals 1? If x equals 1, then y equals 1/4 minus 5/4, which is negative 4/4, which is negative 1. So the point 1, negative 1 is on my line. Now I want to use a slope of 1/4 to graph this line. So I'm going to go up 1 over 4. Notice I just landed on the point I wanted, but let me get another point to graph this line. Starting at the point 1, negative 1, I can go down 1 into the left 4 to get a third point on the line. And when I connect these 3 points using my ruler, I should see that I have a line perpendicular to my given line that contains the point 5, 0. So I've drawn a line that appears to be perpendicular. And remember what we talked about in an earlier lesson. These lines will only appear to be perpendicular if we have equal scales on both axes, which indeed we do in this example. Let's do another one. Now we want to find the equation of the line which is perpendicular to the line y equals -3 that contains the point 5, 2. As I was reading the problem, a little hint came up that's telling me that it's easiest to do this problem graphically. Let's graph the line y equals -3 and see if we can figure out what the equation of the perpendicular line is. So I have some axes here, and I want to graph y equals -3. Well, this is a horizontal line with a y coordinate of -3. So here's the graph of the line y equals -3. Now I want a perpendicular line that contains the point 5, 2. Well, a perpendicular line to this horizontal line is going to be vertical. So let me draw that vertical line. What's the equation of this line? Well, a vertical line has an equation of the form x equals a constant. What's constant on this line is the first coordinate. For all of these points, the first coordinate x equals 5. So the equation of this line is x equals 5. So I can conclude that the equation of the perpendicular line is x equals 5. Now here the directions are a little bit more complicated. We want to find the equation of the line perpendicular to the line y equals 2.5t minus 10 that intersects the line at its horizontal intercept. We're not explicitly given a point on the line, but let's see if we can find it. So what I'm going to do is I'm going to graph the line and determine its horizontal intercept. The first thing I'm going to do is rewrite that slope, which is written as a decimal, in a fraction so I can use the concept of rise over run to sketch the line. So 2.5 is the same as 5/2. So let me graph this line and see if I can figure out the horizontal intercept. So the vertical intercept is at 0, -10. I have a slope of 5/2. So I'm going to go up 5 over 2, up 5 over 2, up 5 over 2. I landed at the point 4, 0. So graphing my line showed me what the horizontal intercept was. So now what I want to do is find an equation that's perpendicular to this line and that intersects it at the horizontal intercept. So I'm looking for the equation of this line. So this is my given line, and this is the line that I'm trying to figure out. So now what do I know about the equation of this line? Well, I know its slope is the opposite reciprocal. So the opposite reciprocal of 5/2 is -2/5. To determine the vertical intercept, I'm going to use the point 4, 0, which is on the line. So if t equals 4 and y equals 0, then I have 0 equals -2/5 times 4 plus b. So 0 equals -8/5 plus b. So b equals 8/5. So my equation should be y equals -2/5 t plus 8/5. Notice on even this rough sketch of my perpendicular line, it does appear that the vertical intercept is 8/5. Let me finish up now with an application. Josh and Leon both drive cars that get 30 miles per gallon, but Josh's fuel tank has a capacity of 18 gallons, whereas Leon's tank holds only 12 gallons. We want to sketch a graph of the fuel remaining in each car in terms of the distance driven. So I already have some axes here set up. We're told to sketch the remaining fuel in terms of the distance driven. I have the information from the problem that we're going to need to graph this relationship. Josh and Leon both get 30 miles per gallon. That means that they're using fuel at the same rate. But their tank capacities are different. So when we're thinking about the vertical intercepts of these graphs, the vertical intercepts are going to be the amount of fuel in their tank before they've driven any miles. Those are going to be points on the vertical axis. So I need to have a vertical intercept of 18 for the graph representing Josh's car. If I look at my vertical axis, I have 1, 2, 3, 4, 5, 6 tick marks. I think I'm going to use a scale of 3. So I have 3 gallons, 6 gallons, 9 gallons, 12 gallons, 15 gallons, 18 gallons. So I'm going to draw the vertical intercepts of both of these graphs. Now let me focus on Leon here for a moment. I have a scale of 3 on my vertical axis. So if both Josh and Leon get 30 miles per gallon, then how far can they drive on 3 gallons of gas? Well, on 3 gallons of gas, they should be able to drive 90 miles. So I think what I'm going to do to make the graphing easy is use a scale of 90 for distance driven. So I have 90, 180 miles, 270 miles, 360 miles, 450 miles, 540 miles, and 630 miles. Now you'll see in a moment just why I labeled things this way in case you didn't see it before. So now I want to plot points. So when Leon drives 90 miles, he's going to use 3 gallons of gas. The next point on the graph representing Leon's car is going to be 99. He drives another 90 miles, he uses 3 gallons of gas. He drives another 90 miles, he uses 3 gallons of gas. He drives another 90 miles, he's out of gas. Let's give ourselves a little bit of room so that we can think about Josh. First of all, let me connect the points, which represents the line representing Leon's car. Now let's think about what's happening with Josh's car. He's getting the same mileage as Leon. So we would expect the graph to be parallel. So using the same slope, the fact that their fuel mileage is the same is what's giving us parallel lines in this example. So the second line is the line that represents Josh's car. So I've done what was asked. I graphed linear equations that represent this situation. In this case, we see the linear equations are parallel. So with that, I'm going to turn it over to Steve, who's going to work many more applications for you.